want to have 8 electrons in their outermost shell. That's their goal. That means they're stable. But as we can look at our periodic table of elements, most people, most individuals don't have 8 in their outer shell. They're short by some amount. So they're going to need to do something. So we can remind ourselves that hydrogen has 1, right? Helium has 2 in its outer shell. It only has 1 shell, so actually you're quite happy. We know that we can donate an electron from one element to another, or from one atom to another. And when you change the number of electrons relative to the number of protons, you now have an imbalance. So remember the atomic number. Let's look at oxygen again. It's 8. That tells you it has 8 protons, 8 neutrons, and 8 electrons. The number of protons matches the number of electrons. It means they cancel each other out, the overall charge. If I mess around with the number of electrons, I now have an imbalance. If I have more electrons than protons, that'd be a negative charge. If I have more protons than electrons, that would be, more protons than electrons would be a positive charge. More electrons than protons would be a negative charge. So we're going to walk you through this. That's why chlorine has 1 more electron than proton, so it has an overall negative charge. And sodium has 1 less electron than proton, so it has an overall positive charge.
Yeah.
And you know the old saying, opposites attract. So now we're going to get an attraction, a bonding happening between them. So, one other thing to look at is what's called the mass number. And that's how much it weighs based upon the number of neutrons and protons. And yeah, they're counting electrons, but it's really insignificant. They don't really come into the formula. So if I have 8 protons, and I have 8 electrons, then I should be able to add up how much they weigh and get a nice little round-off number. Well, the number in red down below is the mass number. It's how much it weighs. And what you realize is they're not whole numbers. They're actually numbers with decimal points, because there are oddballs in the family of each element. All right, things called isotopes. They're like relatives to the atom, to the elements. An isotope is an element, a version of an element, but probably the best way to think about it, a version of the element that has more neutrons than it's supposed to have. So if oxygen's number 8, I mean, I know it should have 8 protons, it should have 8 electrons, it should have 8 neutrons. But I can also find it having 9 neutrons, or 10 neutrons. And it's still oxygen, because it still has 8 electrons, it still has 8 protons, right? It's the number of protons that determines who you are, right? I'm 56 years old, so I've got 56 protons. But I have an imbalance of neutrons. And so I use that word isotope to let you know that we're talking about an element that has an improper number of neutrons, right, in relation to how many protons it has.
That makes sense.
All right, let's look at some of these. All right, have you ever heard of carbon-14 dating? Really? Not many of you? Oh my God, carbon-13 dating? Oh my gosh. Okay. Well, if you've heard of carbon-14, like, well, what the heck why is it called carbon-14? Why is it called carbon-13? Because the 13 and 14 tell me how many neutrons are inside of it. So let's go find carbon on our periodic table of elements, right? There it is, right? It has 6. It's supposed to have 6 protons, neutrons, and 6 electrons. But if you have 1 extra neutron than normal, 7 and 6 are
13.
carbon-13. 6 and 8 are 14, carbon-14. Right? See, they're not counting the electrons. They don't really add to the mass. They're like little goose feathers. They're really teeny tiny. But this is what adds the bulk of the weight, or the mass. Right? And mass is anything that occupies space, like matter. So now I know that carbon-14 has 2 more neutrons than normal. I know that carbon-13 has 1 more neutron than normal. I know that carbon-12 is normal. It has the same number of protons and neutrons. Well, why is this cool for us? Have you ever heard of isotopic tagging? Right? Isotopes are unstable. They are, quote, radioactive. And I can have a machine like a Geiger counter that lets me know where they are. I can trace them. I can give you a shot of an isotope in your arm, and I can watch it follow your bloodstream and figure out where it ends up hours later. Like a little GPS system in a sense. Well, we can also use them to date things with. How old are they? And I haven't tried the video, so keep your fingers crossed. Let's see what happens here.
This is Aaron and Ariane.
All right,
They
well,
turned
they
this
don't block
100-year-old building
commercials,
from
unfortunately.
this into
All right. Does that work? Cool, that works. Does the light switch work? Holy cow. There we go. All right, let's see what isotopes are good for.
How do we know how old something is? For people, we'd ask to see their birth certificate. For trees, we'd count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read
It is the amount of time necessary to take the amount of something you've got and reduce it by half its amount. So let's say if I have, make numbers easy, 100 carbon atoms. Let's say the half-life is a year. It means every year I'm going to have half of what I had before. So at the end of 1 year I have now 50. At the end of the next year I have 25. At the end of the next year I have,
Zero? No.
what's half of 25?
Oh, half.
12.5, right? And then half of a half of a half of a half of a half. So if I know we started with 100 and I've only got 25 left, I can tell you how many half-lives it went through. And if I know how long the half-life is, I can tell you how many years passed by. And right now what they're trying to say is that all animals go around munching on plants, right? You will learn that plants will take carbon from the atmosphere, right, to make sugar through the process of photosynthesis. So now plants have carbon, animals are munching on plants, so I'm now getting my carbon from the plants. Well, plants are getting carbon-14 from the atmosphere as well. And there's a certain ratio, certain balance of, let's say, for every 1 million carbon-12s will be a single carbon-14, like a 1,000,000 to 1 ratio. So now today we can count how many carbons are in a leaf. I can tell you how many are 12s and how many are 14s. And it's pretty balanced for the most part. One of the arguments against carbon-14 dating is you can't assume we've always had the same amount of carbon or the same number of carbon-14s in the atmosphere. And they're right, it has changed. But we also have that calculated into our equation. We've accounted for that. So there's a lot more validity to carbon-14 dating than a lot of folks are saying. So now, when I'm running around munching on, eating on animals or plants, if I'm both a carnivore and herbivore, I maintain that balance of 12s to 14s. I'm alive. I keep eating plants. As soon as I'm dead, I'm no longer consuming carbon-14. Carbon-14 has a half-life. It begins to become less abundant within my tissues. And the older I am, the less of it there will be. So if we know the ratio, and then you find John's corpse, let's say 17,000 years from now, you'll know that John's carbon-14s went through 1, 2, 3 half-life cycles. And then you know how old John is.
I just wanted to point out, because I know that this was confusion in another class I had, that like the carbon dating though only dates how long ago something died, not how old it was when it died, correct?
Right.
Yeah.
Yeah, so
Yeah.
it won't tell
So
you
that-
that I'm 56 years old, but it
Right.
says that I died 17,000
Yeah.
years ago.
Yeah, and
Right.
I just know that that can be unclear.
Oh, okay. Yeah, so now let's look at the rest of this.
Thank you.
and after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.
So, I think it's safe to say that every molecule, every compound, every radioactive element, every isotope has a half-life. Chemicals in your body have a half-life. When you guys get into Bio 241, if you have me, we're going to talk about half-lives of things like nicotine, caffeine, cocaine, and it's kind of relevant right now, so just I want to introduce this idea to you now. Caffeine has a half-life of about 3 to 5 hours. And you want to think about that in terms of your drinking habits and your sleep cycles. If you've ever wondered why it's 10 o'clock at night or 11 o'clock or it's midnight and you can't fall asleep and you say, but I haven't had coffee, since 5 o'clock this afternoon. Mm-hmm. Well, if caffeine has a half-life of 3 to 5 hours and you're like me, and most of my friends say that you can probably pour John's coffee out of the coffee mug and it'll form a pole because that's so thick, right? I want substance to my coffee. Most restaurants don't produce coffee, they produce dishwater, okay? But if I go to Starbucks, right, and you can get a Vende, maybe a normal blend, it's gonna have about 400 milligrams of caffeine. Now, the half-life is 3 to 5 hours. Let's make it 5 hours. That means every 5 hours I have half of what I had before. So let's say I drink it at 5 o'clock. Well, by 10 o'clock I still got 200 milligrams in there. For most of you, that would give you the jitters. All right? Then that means at, 3 o'clock in the morning? That the next 5 hour section? 2, 3? I still have 100 milligrams. Your average restaurant coffee, when you go to like Denny's or Sherry's or places like that, they're around 50 milligrams of caffeine in a cup of coffee. So if one of those cups you can feel, then you're not going to be out of caffeine world until about 8 o'clock the next morning. All right, which is why you start thinking about, all right, if caffeine bugs me, then I now know about half-lives. The half-life is about 3 to 5 hours. You need to start being aware of how much caffeine is actually in what you're drinking. Many